Okay, yeah, thanks for invitation. And yeah, it's nice to back to Seokcheon. So actually, previously people also proposed the varying speed of light. And actually, when I was a student and even probably about 5 years ago, until 5 years ago, I don't believe a varying speed of light. It's a too ambiguous idea. But actually, if you think about the expansion of the universe, especially GR itself is not a global theory. It's a totally local theory. So there's this problem applying the general relativity to the cosmology, which means the entire history of the universe. But after, that's one of the reasons Einstein was struggle about the expanding universe itself. But after the Friedman and the Lemaitre and the Hubble observation, people invented actually going back to Friedman equation was too early, so nobody can really understand. And after he passed away, Lemaitre actually argued with Einstein in 25. And then the Friedman equation is actually, not many people knew that at that time. But after then, it's about 1928, and the 32, the Robert Walker, they proposed the metric which can provide the global structure of the universe. So history was back to the historical is inverse time. But during that time, what I noticed is that when we invent the expanding of the space, then we should have some proposal about the time, global time, cosmic time, because we should guarantee that our observer is a free-falling observer in whole entire universe. And then the proposal and the observation nowadays confirm that the size of the universe is expanding, which is embedded in the so-called as a scaling factor, which is observed in the many spectrums. And then if we want to assume that make sure that the speed of light during the expansion, because this is a wavelength of the photon. So photon is actually stretched because of the expansion of the space itself. So original wavelength, for example, was the 5,000 angstrom. If that was emitted in the early universe, and then if we observe that today, like when redshift at 0.5, for the easier way, if we that emitted at 1, then it's twice is a wavelength nowadays we observe on the Earth. Then if you think about the c, speed of c is lambda. So then if this is changing and it's actually stretched by inverse factor. So no, it's inverse. So then in order to keep this one as a constant, then frequency of the photon should be inversely proportional to the scale factor, or in the language of the cosmology, usually is the redshift. So this cancellation preserves that the lambda 0 f0 is the same as lambda f in any epoch. So this is theoretically proposed as the A, scale factor A, and it's confirmed by the observation. But how about the time? Time is, as the universe expanded, this is so-called as a time dilation. Especially in the guys like in here, usually you guys expert in the GR and black hole, and then you think about the G00 component changing in the metric to have the gravitational time dilation. That's the gravitational effect. This one is a cosmological effect due to the expansion of the universe. So then, do we have any first principle to claim that this has exactly have the inversely proportional to the scale factor? We don't have it. Okay, so it should be come from the assumption that if C is constant, then this is guaranteed. If C is not constant, then this can have a different evolution. That kind of observation can be observed with so-called supernovae data. So I will get back to that. But as you can see, this is the duration of the brightness of the light curve of the supernovae. And if you have the higher redshift, then it has the longer duration because of the time duration. And then this kind of observation can check whether this is exactly inversely proportional to the scale factor or not. So we'll see that. Okay, so that's the main idea. And if you have this kind of idea, then changing of speed of light caused all of the problem about because modern cosmology is based on the GR, but in order to explain the expansion of the universe, we should have the adiabatic expansion. That means the thermodynamics constant, Boltzmann constant, including the Stefan Boltzmann constant, including C, and that also related to the Boltzmann constant and also the Planck constant, and that also we need to be worried about that. It should be changed. So we'll get to that. Otherwise, the Robotalk metric doesn't make any sense. So we'll get to that. So before go to the any deeper, this idea is come from the Robotalk metric itself. It doesn't need any mechanism like the Franz decay or whatever. You don't need any extra degree of freedom to varying the C. I will show you how to derive the Robotalk metric, and Robotalk metric itself, as long as we have the cosmological principle, homogeneity and isotropy in background level, then there's room for the changing C as an expansion of the universe. Okay, so that's the main outline. So let's get to that.
The constant of this line is on assumption thing.
No, in the special relativity. In GRC can be changed based on the metric component, G0, Newton constant, Newton potential.
Yeah, and you could change the Newton constant to G as one of the examples. But you keep the C is the constant usually. Yeah, you could relax the C, the speed of light varying, and you try for all equations from the action.
You need to, yeah. So then that caused also the G changing. I will show you. I also showed how to derive that one from the action principle. Okay. So that's the outline, and then I will show you how to get to that. So Robotalk metric itself require the background evolution should be the overall shape of the universe should be homogeneous and isotropy about the 200 megaparsec. 200 megaparsec means 1 megaparsec is the size of the galaxy cluster, which means about we had 10 to the 15 stars. And then if you have that kind of clusters have about 200, then overall, of course, the universe is entirely inhomogeneous, but even though it's small size. But if that distribution, if you're looking at the larger size, then that distribution looks like independent of the location and any directions. So that's the homogeneity and isotropy assumption, so-called as a cosmological principle. When the Robert and Walker, they derived that metric independently. Then the means we have the killing vector for the rotation isometry and the translation isometry. So if we acting on any general metric to this killing vector to the killing equation to satisfy the isotropy, then the metric is specified in this form. We only have 6 components, actually 5 components, 0, 1, 1, 0. So So symmetry. So we only have the phi component. And then if we apply the translation isometry again, and using the Killing vector equation, Killing equation for that vector, Killing vectors, then our metric now is to get back to the as simple as this one, the familiar one we have for the Robotov metric. So we still have the room for that at specific time, we can rescale the time as like this and make the metric cancel as -1 for the temporal component, 0, component. So this metric is, so whenever we say space is homogeneous and isotropy, that means at one specific time. So this metric, when we derive from the Killing equation for the isometry and the homogeneity, then this is an equation at one single time, okay, at TL. And then in order to extend this one to any time, for the global time, we need to, people propose so-called as a Weil postulate. So we can guarantee that from the Killing equation at T equal TL, ES square line element is just like written as the Robotov metric. This is for the flat case. If you have the Gaussian curvature for the spatial component, then we have 1 over KR squared coming here, and so on. And this is a solid angle plot. So this is true for at T equal TL. And then in order to study the history of the expansion of the universe, we need to generalize this one to TL to the any T. Then, as you can see, back to the robot and the worker time, at the 28, 29, and the 32. At that time, of course, the special relativity is actually people already knew that. So they dropped the C and just put as a C, and then
I have a question. So for a fixed observer, I mean R equal constant.
R equal constant.
In the conventional case, actually proper time is nothing but the coordinate time. So which means that the fixed observer is now actually freely falling observer in our universe.
That's the
But C is actually a time-dependent function. Then is it still possible to interpret?
So that's the missing of about what the bipostulate. Okay, what bipostulate means is this is a time independent. So this is so in the Friedman robot worker case, one of the missing point is usually when people write down this one as and also when I talk to the George Ellis, he also misunderstood this one. And then this is actually testable equation. So in the Friedman robot work metric, BT is actually same as the tau, co-moving observer. And because this is a co-moving observer, this dx3 is actually a time independent. So this is for the light traveler, for the null geodesic, this is a AT CDT. And this is should be same for the AT1 for any time, T1, T2, T2, C2, T1, T1. So if we say time interval, time clock, this is the inverse frequency. So this is the period. If this one is exactly same, globally same, as then this can be the constant. Because this is constant value, independent of time. We do have only changing of this one is a peculiar motion when you have the inhomogeneity in the local gravity. That is about 100 kilometers per second observed in the galaxies. But in the overall shape, for the background level, we assume that this is constant. This is not changing at all. So this is actually, that's the why when people explain the expansion of the universe as a bubble, that time slice in here is should be orthogonal to this hypersurface at T1 to make sure that the time flow at this observer and this observer separated by dx3 should be same. But there's also the expansion due to the AT, but their separation is conserved. Only difference is this background is stretched at the T2 in the hypersurface. So time flow in here is still orthogonal, even though their length is increased. The length increases because A is increased. But dx3 is still same. So P and tau, this is observed free-falling observer. So tau and T in this robot walk metric is same. So that's in the textbook they explain that the cosmic time and proper time for the robot walk metric is the same because this is a constant.
So in your case,
This is not my case, but what I did is in order to if we want to claim that this is just a C constant and just adopt the time variation for the A, then one should have the assumption that this dt scaling is exactly same as the inversely proportional to the scale factor. That's the assumption. It's not the first principle to say. In the same wise, if we claim that this C can be changed, then only difference is now this time interval dt has a different scaling than inverse scale A. So it's a equally same assumption as the general relativity. One can extend this idea to the time dependent or constant. Only difference is the time was the time dilation due to the expansion. But there's no first principle we can claim what's the time the dilation due to the expansion. Okay? It's not embedded in the metric itself, as you can see here. This is a bias, this is a cosmological principle.
anyway, it corresponds to actually rescaling time. Okay? C.
That's you can interpret it as a Lex function. Right. So I will show you that also. Yeah, you can interpret a Lex function for sure. Thank you. Okay. So idea is that because now in order to study the global entire history of the universe, every observer should be at galaxy 1 and galaxy 2 should be free-falling observer. That means that their time shouldn't be mixed. That means that there shouldn't be any translational motion on each hypersurface. So that's the co-moving observer, and then there shouldn't be any changing to guarantee this. And only time changing is along the temporal axis. That's what we standard model do. And that's how we can interpret. Usually in the cosmology, we adopt that scale factor is a change. We can measure the scale factor, mass density, pressure, and temperature, which is a given values. And then they are redshifted as A changed. And assume that C is constant. Then after that, in order to guarantee the adiabatic expansion, this one also should be constant. But if we assume the release that assumption, then this one can be changed also. Then also we need to check whether these guys also can be changed as an expansion of the universe or not. On each hypersurface, they are given numbers, so it's constant. So that means it satisfies all the local theory, local physics, because we already know the electromagnetic and quantum mechanics is that there's no violation at all. So at each given time, today on the Earth, or maybe billion years ago on the Earth, the constant C is constant on that hypersurface. Okay, so as long as you put the C as a function of the scale factor A, and sorry, this is typo. Okay. Okay, I will show you.
Very simple case. One can think about that theory, action, with heading C.
I will get to that. Okay, just hold on.
If you start that,
I'll show you that. I tell you. I told you that's in the slide. That's a pay attention. So that's a theoretical approach. And then if observation doesn't agree with this, even though there's a possibility for that bearing speed of light, if observation doesn't differ, then we just throw it away. And then we do need to check whether this is really exact or there is a relation. Some So actually, if there's the slightly changing, then instead of 1, there can be some changing in the proportion as some deviation from the constant velocity case. So observationally, it's important whether there's the beta is 0 or not. That's what the observation need to do. So that's what we mean by 1 plus beta. As long as so this one is I adapt from the supernovae last year in the dark energy survey. This is gamma ray burst and this is quasars. And this is actually there's a 4 channel, 4 frequency, 4 different frequency levels. And this is a number of supernovae, number of gamma ray bursts, and number of quasars. And this one, usually the quasar was actually quite pessimistic about the changing of any. So quasar usually totally disagree with the standard model even. So usually quasar data is actually no evolution. So no time dilation. That was back to the 1969. So at that time, people argued that maybe standard model, the Big Bang model was wrong because they cannot get any time dilation due to the expansion. But nowadays, this kind of a job is actually, as you can see, the gamma ray also doesn't get close to 1. But when they design the observation data based on some meaning, it's a kind of a modulation, then they can get to be something meaningful to the close to 1. But these 2 observation is not that reliable. But supernovae itself is really can show the time dilation. And this one is after we remove that expansion effect, everything looks like a coincidence to the same time, because this is a light curve. After supernova reach to the maximum brightness, and then they fade away. This duration is same for all the supernova type 1A. That's why we call it as a standard candle. So this one is reliable, and then what I found is their data in the I-band. This is most reliable data. And they do have some meaningful 1 sigma level about the deviation from the standard model. So that's was one of my paper claim about the importance of their observation measurement is that there's the possibility about the bearing speed of light. Instead of their purpose is that they claim that they confirm that standard model relation of the cosmological time dilation using 4 channels, 4 frequencies. But what I emphasize to them is actually this is a more reliable data, and this is a more meaningful to claim that there can be some chance for the showing the deviation from the standard model, constant velocity motion. Okay. Not yet. So this is theoretically why I confirm that this is what we have. So now compared to the traditional one, instead of put the constant or put y as a 1, I just room for that the t or c as a function of time. Then from the constancy of the co-moving observed distance, there's 3 possibilities, actually 2 possibilities. C can be constant as long as time dilation is inversely proportional to the scale factor. Or if this one is not exact 1, but there's some slightly changing, then C is need to be changing. So this possibility is equally same. It's possible. There's no reason this one is preferred or this one is preferred in general relativity. Based on this is even in the closed black hole, you can usually increase your speed of light can be infinity. But this is actually not from the local gravity effect, but this is just due to the expansion with the size of the wavelengths. Then time frequency also should be have some changing. Okay, so but the cosmological time dilation is not derived. It's not a first principle theory, and it's just derived from the assumption of the C is constant. So equally, we can release that assumption, say that it's not true. If there's some deviation, then C can be changed. So that's what we claiming here.
Question?
Mm.
Can you go back one more
Okay.
So I think I'm perfectly fine with working with the metric with T dependence in the GTT component. I mean that there's nothing wrong with that. So the reason that I was confused with is usually when we say speed of light is a constant, that means if we really took the freely falling coordinate system, freely falling observer, that means we are using the field line and then look at the coordinate system where the metric is given by C, constant C squared, dt squared, dx squared.
Not constant.
So
So
what I mean is you're just using the metric with T dependence on the dt square component. That's fine. I mean, but that's not freely falling coordinate system. That's what I'm saying.
So this is there's not a preferring yet, isn't it? This is just come from the background itself is homogeneous and isotropic at single given time. And then what Robert Walker did is now in order to study the entire history of the universe, now we need to guarantee that every galaxy should be the free-falling observer. Then time flow should be same. That means there's no translational motion on the same hypersurface. Then we can extend this time as a global time. That's what bi-postrate means. So then this one was a constant and this one was a constant given number at a single time. And then if we say that it's a free-falling observer now have the different expansion on their size at each hypersurface, then we can say this one now is a t, the general function for the global time t. And then
What I'm talking about is more just pure mathematical statement. So our O is described by some manifold, and then for freely falling observer means the locally inertial frame, and that is defined by the coordinate system where the metric is given by Minkowski metric by definition. And there C has to be constant. There's nothing changed here.
No. A is constant, C is constant on each hypersurface.
What I mean is, let's say you took
Right, then now you're looking at
that
that.
is not locally inertial metric at all. You have to choose the metric where the minus C squared, D squared plus dx squared, dy squared, dz squared. If your metric is given by that, that's your locally inertial frame.
So
That's the definition of manifold.
what Minkowski means that you have this can be just a spatial curvature, so it doesn't matter. So you can just put the k equals 0. It make the argument simpler. Then this DL3 is just a distance between two observers in here.
Why you are thinking about two observers?
Infinite number of observers. We are talking about the relative motion between the two galaxies. When you're talking about the free-falling observer,
When you talk about coordinate paths in a manifold, we pick one point and then find the coordinate paths describing that point.
Right, no questions, it's not beautifully satisfied.
Yeah, right. So what I mean is, you don't need to, when you think about 2 points, it's not the thing when you do in describe manifold, right? When you describe manifold,
free-falling observer means that the time is perpendicular to this hypersurface at t equal t1.
why are we thinking about hypersurface? That I couldn't understand. In the four-dimensional Lorentzian
This is a robot work metric, specified
Yeah, so-
the robot work metric.
So in the beginning, I'm completely fine with generalizing Robert worker metric by allowing for T dependence in the DT square. I'm okay with that. So of course, I mean, then your analysis, I want to follow. I mean, that's completely fine. So the only reason that I'm confused is when theorists usually say speed of light is constant, that's not the statement related to Robertson worker at all. I mean,
It's not.
completely independent of that.
It's not.
Yeah, we start from four-dimensional Lorentzian manifold, pick a point, and for that point around that region, we can define coordinate system, which is homeomorphic to Minkowski space. Minkowski space, by definition, metric is minus c squared dt squared plus dx squared dy squared dz squared. So there C, what I'm telling is that C has to be constant. That's
At the local point.
yeah, at the local point, exactly.
Then now, that's why people working on the robot work metric, at the very beginning, I told you,
Yeah.
general relativity is a local theory. It's there's no room for the study the global structure of the universe. And then we have only one solution, time-dependent solution. That's a robot worker. Actually, de Sitter is also actually just the robot worker.
Yeah,
So that global structure of the universe should be isotropy and homogeneity means that at each single point time slice,
yeah.
they are Minkowski. This global, the three space plus time coordinate itself is Minkowski at each single time. And this hypersurface has no translational motion. Background itself, somehow they stretch. The observer in here, they don't have their relative, this peculiar motion is irrelevant. That's due to the inhomogeneity of local gravity. That's about 100 kilometers per second. This expansion speed can be faster than speed of light, for sure, isn't it? Because of their separation between the two galaxies is due to the expansion, which is nothing to do with the causal effect. So expansion between the two galaxies can be just the Hubble times the distance between two, and this is the expansion. And this can be much bigger than the speed of light, as long as this distance is much larger than the inverse of the Hubble radius, isn't it? So this argument is only true for the robot work metric. This cannot be generalized to any black hole solution, either any local theory. This is, as I beginning, this argument is we talking about the entire history of the universe, and then only solution we do have is robot work metric. So your argument is if you generalize to the manifold, then I cannot guarantee. I cannot even define the C at all because time is keep changing. We cannot define the global free-falling observer. There's no way. So this is the only solution people can guarantee that in the entire history of the universe, every observer is a free-falling observer. That's the robot work, what robot work metric tell us. So it's a very specific solution. And then what I told you in here is in this specific solution, C cannot be necessarily constant, but there's room for that can be changing due to the expansion of that. Okay, thank you. Okay. Okay, thanks for the so
You mean that here, so the metric, you could make that kind of answer regardless of the homogeneous of isotope.
that's a starting point. That's a starting point. And then now, if you see is changing, now we need to start to worry about everything from action and also the adiabatic expansion related to the Planck constant and the Boltzmann constant. So I will get to that. It's too slow. So let me jump a little bit. So the first thing we should confirm that if C is changing, then this is a Big Bang theory is based on the adiabatic expansion. That means entropy, the thermodynamic first law, energy conservation, and entropy increase in the second law, thermodynamics. Then in the thermodynamic case, so dq is d plus dw. So adiabatic expansion means heat doesn't change it. So heat changing is 0. Then the internal energy multiplied by volume, including this combination. So if C is changing, then dq itself now including the changing of the constant. Then means that the temperature of the photon now have the deviation. This is what we observe today. When we claim that C is constant, then we have this relation. If C is changing, there's room for the sigma can be changed. So the constant can be changed. Then this changing can be observed in the CMB. If we have that kind of deviation from the exact inversely scale factor proportionality, then this one should be observed if this is the case.
Excuse me. Epsilon gamma equal proportionally to temperature force.
This because
How to get that formula?
this is actually you can interpret it
When C is time dependent.
okay, there's a deviation also. If you have a C is changing, then there's also deviation. So
It will step up Boltzmann law.
actually we need to derive from the Bianchi identity because the left-hand side for the geometric part is for the curvature part of it. Curvature
I mean, how
conservation.
to relate the energy density and the temperature through the Stefan Boltzmann law when C is time
It's a
dependent.
Boltzmann equation. You need to solve the Boltzmann equation.
But Boltzmann equation should be derived.
No. Yeah.
From the side.
T mu nu, T mu nu, you can derive from the fluid approximation or step the thermodynamics. So this is a photon, so we can have just the
Original formula was derived by assuming C is constant.
right. So if the C is changing, we need to rederive this one.
Yeah, rederive, then we
Yeah.
get that.
Yes, they are. No, not this one. It's this one is okay. This one is still okay. What you need is you need to do this one is for the E and dV for the dP, dE. So that's this is an energy density formula. And if you adopt the same thing, if you adopt the Bianchi identity, then previous equation, continuous equation now is this one. But if the C is changing, you have an additional correction coming here. That's in my paper, but if this C is constant, this is 0, and for the photon case, this is 1/3. So easiest way is you can just change this one as a dT d log A. This is you can change as a dT d log A, d log A, d log. So this equation now became a d log A, d log minus 4 is this one. So if we integrate them, then rho is rho 0 to the a to the minus 4, and that's the rho 0 t0 a to the 4. So you can just change it to the t is t0 a to the minus 4. So if you plug in back to here, you have the t to the 4. That's how you can get the t to the 4 equation for the photon. This is a Bianchi energy conservation, Bianchi identity.
When you think about the different, the C varying to the metric ansatz with C varying, and maybe you could drive the.
I will get to that. I will get to that.
And
I will get to that. Okay.
something is.
I will get to that. Okay. From the action.
You derive the thermodynamic.
Yeah, it's all over there.
And each local frame.
So, right. And then if you see at the given time, on the hypersurface, and then let them change it. C change it, then you need to worry about this kind of a combination also need to be changed or constant. Because this one can be changed. C can be changed, but if you have the combination for HABA C is constant. So if C is changing as a function of time, as a function of scale factor, but it's a HABA is also changing as a minus b to the 4, then this HABA's combination C is constant. That's what I did. Okay. So that's why I call it is a minimal extended model as a varying speed of light. If someone give up the adiabatic expansion, then HABA C relation can be changed. But in here, what I want to do is I want to preserve all the local theories, thermodynamics, electromagnetism, and the special relativity is all same when C is changing or not. Then we need to worry about all the rest mass and the Planck constant and the Boltzmann constant. We need to be worried about the changing of that due to the expansion of the universe. So I will get to that, okay? Okay, so I will show you. So here, as you said, if C is changing, then we need to rederive everything. But as a said, if we derive this one on the local hypersurface and then generalize that one to bearing, then we need to worry about the effect to this one. And then as long as we matching that one preserved, then it's okay. The reason is that deviation from the adiabatic expansion is negligible in the observational. So we believe that universe should be expanded adiabatically. That means if C is changing, then this guy should be also changed in order to cancel the C variation. So HABA C combination is better to be constant also the entire history of the universe. So if C is changing as a to the E over 4, then this one should be inversely powered to the C variation. Then HABA C combination is constant through the entire history of the universe. Okay, KB is a constant in the case in this combination. So that slide is also be there. And then here, so if you have the action now, it's Einstein constant, the C to the 4, C4 over A pi G. If this one is C is changing, then this Platonic term can have give us some boundary term by doing the derivative to this guy. So if kappa, so the C4 is changing, then we have additional term than the GR. Einstein field equation will be changed.
Yes, right.
So in order not to have that one, then again, the Einstein constant is combination for the C4 over G, A pi G. So if you have the C4 is changing as a power of B over 4 for the G, C, then if G is changing as A to the B, power 4, then Einstein constant itself is a constant, the combination.
The constant G.
No, Newton constant is changing, but that,
What is the constant?
because if you have this is changing.
Kappa.
Kappa is the,
G.
yeah, the kappa is the Einstein constant, so it's a C4 A pi G.
Yes.
So if only C is changing and the G is not changing, then we have the boundary term by the derivative to this one.
Okay.
So that will acting as a effective matter term, scale, energy momentum tensor term. So I don't want to have that. So then C variation induces the G variation as a power to this one, power 4 to cancel any variation.
So you keep the kappa equal constant.
Otherwise, we have that term as an extra source term.
So the C and the G could be any.
Okay. So I will show you how many quantities should be changed in the table.
Something different. I mean, when considering the varying G, so we could use the relativity theory and you.
That's different because that is a really dynamical source.
Yeah, yeah.
C is coming, so inverse is G is a pi. That's a
Also,
scalar field.
One could use the theory with bearing C and bearing G.
Sure, sure.
Yeah, it's one of the modified.
You can do that based on
But in
purpose.
your case, C and G could be varying, but the
Combination is
should be
not
constant.
you know, because the current observation is very close to the well matched with the lambda CDM. So if you want to propose a model which is exaggeratedly changing, deviate from the standard model, then that model is already ruled out easily.
So because of keeping the K equal constant, there is no problem on the equivalence principle. Is there any problem on the equivalence principle?
No. Because free-falling observer in here is guaranteed as long as what bi-postulate mean is if you don't have any motion on the translation on the hypersurface, spatial motion, as long as the free is so among the four velocity, as long as you have the zero, the spatial velocity, then it's okay. It's a look because tidal force is all related to the not the perpendicular. So
okay. Actually, I have a question about the previous point about HRC being constant. So is that so my understanding is that one of the constraints on varying constants is these long-lived nuclear isotope decays that they show from those experiments that some constant should be constant for some I forgot how long, but like millions of years or long, some billions of years maybe. Is that why you want that combination to be constant, or is that the combination that appears there?
about the Oklo.
Sorry?
Oklo. You're changing the fine structure constant, isn't it? The alpha case you're talking about.
Yeah.
Alpha, E for Havasi. The combination.
Right.
So the previously it was a quite hard issue. Is that we have about even 10 to the minus 5 variation to the quasar, and then up to 10 to the minus 7. But nowadays people usually claim it's 0, no changing at all. So, and then also the Webb et al. At that time they published so many science papers, and then later on they claimed that their finding was wrong after publishing so many papers on Nature and Science. So nowadays people usually claim that bearing alpha is negligible, unfortunately. But I have that issue also about that. Maybe if I have time, I'll talk about that. Because finding alpha, bearing alpha is 2 different methods in the observationally. And then in the Bering Sea scenario, one method can be show the null changing in the alpha. And the other method can show us some changing in alpha. So, but that paper doesn't publish it in I rejected by the referee, but he don't want to accept. So
can I ask another way actually? Basically my concern is is there any independent way to constrain variation? Because you have to keep H bar.
Right. So
you constrain the variation of H bar.
That's also I want to need to keep thinking about the observational method, any independent method for that. But of course, people usually have the generalized uncertainty principle, but that's for the local observation. So I cannot say talking about in the past.
H bar is not entering into the transition lines of some issue.
There's also an issue there. So I will tell you. Okay, so the reason I call it this one is a minimal extended is the non-minimal case. Maybe you can just claim that C is changing and let others don't care about any relation. But what I want to confirm that the local physics, we know that this is where we cannot find any violation. So the special relativity and the electromagnetism and thermodynamics should be satisfied even in the C is changing. Then as is show that G need to be changed and the lastness is also need to be changed. And then also consistently, when you derive the Einstein field equation, this relation is also derived consistently. If you put into that the C variation, then this one is also automatically obtained from the Einstein field equation. And then they guarantee that the energy, rest energy is same, even though C is changing or not. And same for the lambda wavelength and the frequency is only changing this way, and the permeability and the permissivity need to be changed in order to. This is in this paper. This is about 80 something pages. So I showed all the derivation out of in this one, in this paper, in the 2001 paper. So you can refer that. And then also the Planck constant and the Boltzmann constant as the relation. So not only the constant, physical constants, but also the physical quantity can be time evolved, as we have in the. So this is one example how we can get the permeability and permissivity time variation in this model. So compared to the traditionally, actually, why people propose that not too early, but around the 80 and the 90, people try to overcome the inflation model. So in order to introduce the scalar field, the only idea in the inflation is to solve the horizon problem, aging, oldness, and the flatness problem. Then that means C over AH, Hubble radius. As long as this is decreased, then we can escape from that problem. So in order to have that, solve that problem, not only for the acceleration expansion, but if C is changing, then one can solve that problem, the black hole, the Big Bang problem, with the oldness and the flatness problem. So that was the original motivation in the 80s. People proposed the C changing. Then they tried to make some mechanism. What should be the constant C? And then they probably coming from the Bianchi, the Brans-Dicke type is the most first come idea. But here, what I want to emphasize is that robot walker metric itself already has room for that. C can be changed. And then it depends on your extension of the model. If you want to preserve the older local physics, then we need to be consider about the all other physics quantity and the physical constants also need to be changed due to the C changing. Okay, that's how we get to that.
You show the modified visualization.
Oh, that one probably.
I mean, you show the details firstly. And if you show the action and the Einstein equation and the metric ansatz and modified the visualization and detail.
So that everything. So that is actually same. Everything is the same. The process is all same. So deriving the Einstein field Einstein tensor first. So then you need to derive the R mu nu and R. And then only difference in here is everything is the same as the usual case. But when you have anything like this guy in the, so this is twice of the metric. So we have the whatever it is. We have the derivative that we have one. This one is already have the temporal derivative. So this one including the term like the t, the a, something like that.
I mean, you could use some ansatz.
No, ansatz is a robot walker metric.
Yes. Then if you show the modified field equation after showing the metric ansatz,
So
and
everything should be derived.
You could then one could more clear.
Okay.
So you are
Because it's the same process as a standard model. So we have a metric G nu nu is the same as a standard model. There's no derivation. If you have the special curvature, you can add that one. So you can just put a flat case for the simplicity. And then you derive the, of course, and so on, whatever. Then one thing in here, only difference in here, when you derive the, looking at the temporal one, here, this one is for the G11 case, G110 case, we have C, 1 over C, 2AA dot, is it? For the gamma. So when you derive the Riemann tensor, then you need to derive this one more. Then what have is, there's the term, 1 over C is still there, but we have this term. So there's one half in here, so then this one. Then compared to the standard case, you can just flip this one out. But in this case, what you need to do is in your derivation, you have C over C squared, AA dot, plus standard term. So you have the additional variation term in here. So you need to derive all the R mu nu, R, and to make the G mu nu. Then at the end of the day, what we have is we have the same as the over top, the Friedman equation. Summation for the everything. So this is rho m, rho r, and this is scale factoring as 8 to the minus 4, and if you have the lambda, then this constant, and then the correction term in here is putting in here as like this. That factor is coming from this is under how they change it. So then if you have this kind of changing, then compared to the standard model, you have this kind of correction term. So that's why in this case, the Hubble radius, even though C is changing, Hubble radius is not changing because C over AH in this model is now, A is the same as the standard model, but H itself is now changing to the standard model is this one. So standard model plus correction term to the A to the B over 4. But C in here is a C standard model is constant, but also changing correction term in here. So Hubble radius in this model is not changing. So it doesn't cover the early universe, the idea. So inflation should be there also. Nowadays, nobody wanna kill the inflation because it's a seed for all the structure of the CMB and the large scale structure. So it's still consistent with the standard model. Even C is changing, inflation model is still same. With C changing or not. So everything in here should be, we need to derive, this takes about 1 year for me to derive all the equation and the cross check for the everything to satisfy, and then of course, yeah, so I need to derive everything all together. I can just say C is changing and then that's it. I cannot do that.
If everything is the same and only changing the time component of the metric, then I think you said that.
Time component metric is also the same.
I mean that it's the same, and I think if I remember correctly, you said it's not the same as the Leb's function.
You can interpret it in the difference in the Leb's function. Yeah, I will get to that also in the last one.
Why can't we just say it's an independent diffeomorphism of time, not varying of the still right? Why should we?
So this effect is at each single hypersurface, manifold preserve their shape. There's no changing. Only changing in here is due to the background expansion. Lambda is changing. The wavelength of the photon itself is different today and in the past.
I mean, what I'm asking is
So background shape is not changing at all. The metric is preserved.
It's all preserved. So
Mm.
at that time, when I go back in time and maybe somehow measure the speed of light, wouldn't it be just C?
It can be different, right?
It is just because the time evolution itself.
Time should be, we should measuring the global time. So time itself is all the way through is equal, but only difference is a clock rate at each hypersurface can be different.
Exactly what I'm saying.
Mm. So time clock rate is can be different, and then you can interpret that one as a lapse function.
Yes.
So like, but not necessarily be the manifold or whatever. Okay.
So can I ask a related question? Maybe similar is can I not then define the new time coordinates?
Then everything is keep repeating. So at the very beginning of the robot talk metric also, there's room for the rescale the time. So then after you fix that time, then everything is consistent. So you define the T as a CT as a T, but now if the time clock rate is different, 1/A relation is changing, then you have a new kind of different from the one vector in front of the T. So it doesn't matter for the rescaling of the time.
Right.
What I was asking was, if I measure the speed of light today and tomorrow, will it be different?
Right, in this model.
It will be different, then it's not a rescaling of time, right?
No, but so at each single time due to the expansion of the wavelengths, if your frequency, time rate is changing inversely proportional to that stretching of the wavelengths is not matched, then you have a C is changing. So we don't know whether it is true or not, isn't it? So can you get to that later? Yeah, because I probably also. I still have too many, so I will probably jump to. Okay, so this is all observation. So same argument about in order to confirm whether C effect, changing C effect is there or not. Previous observation is, as you can see, is the measurement is error bar is too huge. So this is a 1 sigma, 2 sigma level confidence level about the changing C. But as you can see, it's okay whether you say C is changing or not because the error bar is.
The vertical axis is speed of light.
So it's a C is the vertical line is 1. No, this one is for this value. So
D is
So this is inversely proportional to the time, and this is actually show that this is a different age range. So this is a little bit slightly different, but so this is a theoretical value. The solid line is the constant C. This is a changing C, and this is 1 sigma level. And then observation is okay whether you say it's a varying or not. And this is last year one. And then this they have the 4 bands means 4 frequency the observation. And I band, only I band show that is deviation from the standard model. Means the C can be changing. So I emphasize this one, and the referee was that the guy in the group, observational group. So he complained why you emphasize, and they already knew that this is a more reliable data. So I claim that this is a more reliable data, and then that meaning is actually quite significant for me to confirm that to check whether C can be changed or not. Then he asked me to add all others. And just show that not only emphasizing the bearing case, but show everything. So that's their data. And then this is a possible way from the data. The C can be smaller than now, and G can be smaller than now. And this is also prepared by some structure formation, large scale structure formation data, but not much emphasized. It can be error bar in observation is huge, so But if you wanna put some meaning, then it's close to that. The structure formation still prefer the non-standard model, and this is actually G smaller than Newton constant today is preferred by observation. And this is also checking whether there can be the direct measurement of the Hubble parameter using some passive elliptic galaxy model, galaxies, and then if there's the effect, then it can be measured. So there's another MNRIS paper show that because error bar is huge, so currently we don't have a way to distinguish the standard model from as you can see, the data is all including this is the standard model, and this is a time-varying case. So everything is included. So it's too early to say the varying speed of light model is preferred than standard model. It's too early to say that. But if there's some room for that the data can be decreased and within this side, then standard model can be pulled up. So it's a hope, personal wish. And then as you can see, if you see is changing, then this is most of the observation we use in the cosmology. Big Bang nuclear synthesis, cosmological microwave background, and the Sunyanseng-Zeldovich effect, baryon acoustic oscillation, supernovae, and the gravitational wave, Hubble, strong ranging, and alpha. That's the you mentioned to be the time-varying alpha case. And details is in the long paper, so you can check. But even though there's the changing, again, decay rate over usually in the Browns decay theory, they also usually use in order to cover the BBM problem in the standard model. And the reason is that they have the changing in the history of the Hubble expansion. And then this is a decay rate of the nuclear. But in this model, even though this is changing, the changing is about this factor, and that is also given in the decay rate. So my model is actually same as the standard model. So there's no advantage to have that bearing C, not like Browns decay theory. So it's not good. CMB have some deviation. So I can have some difference in the changing in the last scattering epoch. So usual standard model is last scattering decoupling epoch is about 1100, 1100. But if you have the B changing, then the last scattering surface can be changing about 100 difference from based on what's the B value. If the B is this is 0.01, 0.02, something like that, plus or minus.
So you can summarize quickly.
Right. So I should get to that. So this, if you want to see more detail, then this part is for the interpretation as a Left function. So again, each slice is a Minkowski, so you can say that there's the interpret as a Left function as a standard case. And this is the Einstein equation you can derive for the perturbation. So this is I submitted yesterday. And then there's, if you have the sum.
Do you have an equation motion for speed of light C?
There's no.
Because C is a
mechanism.
dynamical variable.
Not in this one. So there's no source for the mechanics of the C. So here, what I did is that if A is expanded, and then
You can vary from in the Einstein-Hilbert action.
that's the gauge. So if you in the perturbed level, isn't it? You're talking about the perturbed level or background level?
So you are regarding C as a dynamical variable.
No, but the C and G combination is cancels. So I don't have that. The Einstein constant is a constant. So I don't have that variation term. So if there's no mechanism for the how the C can be dynamically changed. I don't have that in this model. So then changing C have the effect to the dark energy mass density contrast and the Newtonian potential. But the differences is compared to the standard model is only 1%. And this scenario is only 2%. This is for the super horizon model. So the more reasonable region is this one, about 2.5 differences. So it's very challenging. It's very small, tiny change. And for the Newtonian potential, it's the same. And this is the one question bring the spoken about the when you measure the redshift. This is we use the Lindbergh energy scale when you're talking about the spectrum from the galaxies. So then there was a change. So the measuring the redshift can be a little bit changed. So it's also changing. So if B changed, then the changing in the redshift measurement is about maximum. It can be the 3.5%.
The problem is that today you measure the redshift assuming that
C is constant.
so you need two independent measurements. So how do you get these measurements? You need two independent measurements of the
Because
redshift.
we can measure the wavelengths at today. Isn't it?
Yeah, I know. But
That's a stretched one.
you see for instance, the absorption line
Right.
in a different position.
Right, exactly.
But usually you assume that quantity is, the speed of light is constant and you
So-
measure the redshift. But now if the speed of light is changing, you need two different independent measurements. Otherwise, how can you get the limit?
So because we in the today we have a C value is a constant value, and we know that the spectrum line exactly what's the wavelength it is. And in the previously the wavelength is stretched. We know that, so that's how we measure that. They assume that when they are emitted by tracing back, by changing that wavelength in the back that time, and then that calculation is from the Lindbergh energy, and then this energy is also related to the Hubble that touch the changing in this value. This is today's value. This is when they emitted. So we should including this effect additionally, in addition to the redshift change, wavelengths changing. So this has some additional modification, and then that effect is plugged into here. So this is measuring in the laboratory, and then that comparison to the just the today's value. So I asked them to the DESI group. They need to also including this changing in the redshift measurement when they analyze their data for the time dilation in order to be more
I was just
consistent.
wondering how you can obtain, how you can measure, in the sense that
We should
today-
assume. Yeah,
in other words, you get the redshift, a different redshift.
exactly. Right. So
So how do you know?
the one claim is maybe different than in this model. So that correction term should be considered, right? Yeah. Emitted, that's that amount of changing. It's a small time, about 3%, so they don't care too much. Okay, so last one is that in order to, nowadays the people talk about the Hubble tension, but I don't care much about the Hubble tension because I believe it's come from the systematic of each observation, and people already knew that when Planck data released first at the 2016, we already knew that their selling point was that, because at that time people complain about why people do the Planck, because WMA already measure everything. So if you don't measure the polarization, measuring the temperature is meaningless. But at that time, their selling point was omega m was larger than the Planck data. So omega m value, the Planck is 0.32, and omega m for the WMAP was like a 0.8. So they claim that, oh, we have more dark matter, which means that dark energy is much less. So age of the universe is longer than the WMAP. That's their selling point about to escape the brain. But what observation really do is they cannot measure the omega m, omega lambda separately. What they measure is omega m h square and omega m h square. Then this H value WMAP was 0.72, and the Planck, this one was 0.68. And if you combine these two, they are same. So about more than 10 years ago, they already claimed that omega m is larger in the Planck. That already means that the H value is smaller. But people at that time don't care much because except the CMB, most of the data from the large scale structure or BAO, they prefer this one, WMAP data instead of Planck. So many theorists, when they analyze their model, they adopt the still Planck, the WMAP data instead of Planck. But that passed about after 5 or 7 years, referees forget about this one, the truth, and then they just keep complaining about why you analyze your data with WMAP instead of Planck. Planck is a more recent data, and then so after then, every paper now they heading to the omega m is the same as 0.32, and then naturally that means H should be 0.68, not the 0.72. So I don't think that really the matter. But as you can see here, H value can be changed in this model, but that's not my selling point. So, but because in order to really study that WMAP data, then we need to change the order of Boltzmann equation in the code. It's a huge program, so I still struggle with that. And then if someone want to have the extended model, then probably one have the different relation between C and the HABA or other constants and so on. So I think that's it for today. Okay, thank you.
Clarification, the Hawking argued that the expansion speed during the inflation is greater than the speed of light.
Superluminal.
Yeah. Is correct in your viewpoint?
Oh, actually, in mine is cannot say anything because mine is the same as the standard model. So we do need a superluminal expansion to overcome the ageness and the planes problem. But then the origin of that is not coming from the changing C, but I need to just adopt the inflation model, inflaton or whatever, other the inflation mechanism. Because the C changing doesn't change the Hubble radius in my model, so it doesn't help. So early universe is the same as the traditional one in my case.